Hello everyone, I'm Jure and I'll talk about counterexamples for optimal scaling of Metropolis Hastings chains with rough target densities. First of all, I'd like to thank the organizers for the opportunity to present my research here, and I'd like to say that this is joint work with Wilfried Candle. In case I lose you, there's two take-home messages I'd like you to remember. First, that the guidelines for tuning MCMC do not hold in general if the targets are not smooth enough. Things like accept roughly 1/4 of proposals when using random walk Metropolis. The second thing I want you to remember is that this isn't just a single contrived counterexample. This phenomenon is rather general. There are generic classes of target densities which exhibit anomalous kinds of optimal scaling behavior. We would even go as far as conjecture that this sort of thing is typical in the presence of insufficient smoothness. So start with the target density on Rn that we would like to sample from. We do that using random walk Metropolis algorithm, which evolves according to the following evolution rule. When you're at the point xk, you simulate a proposal by adding to xk a random increment that is given via symmetric symmetric distribution on Rn called the proposal distribution. You then evaluate this alpha, which is the minimum of 1 and this ratio here. And finally, you toss a coin with heads probability alpha. In case of heads, you accept the proposal and you move there. In case of tails, you reject the proposals and you stay where you were. What this does is that it generates a target, it generates a correlated sample that is distributed increasingly according to pi. And the valid question here is how to choose Q so that this works as fast as possible. This is a question that is very relevant. But already it's too complicated question, so we narrow it down to just normal proposal densities. So if you have a proposal density that is normal, just an uncorrelated normal where you're only allowed to vary the variance, how should you choose the variance of the proposal to make the random walk Metropolis run as fast as possible? If you choose the variance too big, then you will propose a lot of proposals into the tail and there will be a lot of rejections and your chain will not move much, as is in this picture. If you will tune the variance too small, then you will see this diffusive behavior where a lot of energy is spent on like random walking on the spot and not really exploring the state space efficiently. It's not hard to see that something in between performs the best, but can we say more than these heuristics? We can. Consider the following toy setting. We have a density pi on R this time, and we have a sequence of random walk Metropolis chains. The first chain lives on R1, the second chain lives on R2, the third chain lives on R3, etc. And the nth chain has a target equal to n copies of pi multiplied with each other together. And it has a proposal that is a normal proposal in Rn with the variance that scales with n, and it scales according to this formula, L squared divided by n, where L is a constant. This is the classical result by Roberts, Gelman, and Gilks that says the following. If you take the nth chain that I just described, you make a continuous time process out of it, accelerate it n times, and look only at the first coordinate, then these processes converge weakly as n increases to a Langevin diffusion. That's this diffusion, which lives on R, has pi as a stationary measure, and has this HL parameter that describes the speed at which it moves. The idea behind this result is that the higher the value of HL, the better the diffusion explores its state space, and hopefully also the random walk chains converging to it also explore the space as fast as possible. Now HL has an explicit formula that is not relevant here, but what is relevant is that it can be optimized, and it turns out that HL attains the highest value precisely when this portion of proposals are accepted. So when 23% of proposals are accepted, that's when your random walk Metropolis chain works best. That's the famous guidelines derived from this result. then this result doesn't come for free. It, among other assumptions, it requires two derivatives from the target. The target has to be C2 smooth. Now, do we need that, is the question. Wilfried, together with Giacomo Zanella and Mylène Bédard, they have shown that actually one derivative in n a bit is already enough. And then these people in the same year have shown something that I will interpret here as pi can be non-smooth of a measure zero set, meaning that Laplace density or anything that has a finite amount of spikes is also okay. Then the next question is, can we move beyond C1? And we can't. That's where our research comes in. We show that for any h, for any h arbitrarily close to 1 is not good enough to recover the classical result. Now, to understand our counterexample, we need to introduce fractional Brownian motion, two-sided, not indexed by time but by location in R. So fractional Brownian motion is a Gaussian process with this covariance function. If you're uncomfortable with it, imagine h equals 1/2, in which case we're dealing with Brownian motion. The relevant property here is that that almost surely paths of fractional Brownian motion are alpha holder for any alpha less than h. And we're looking at random targets, random with respect to fractional Brownian motion realization of this form. So what are they? They are Gaussian density perturbed by a path of fractional Brownian motion. They look something like this. This is one generated example. And at this stage, we can ask ourselves, if I take a realization of fractional Brownian motion and I construct this target density, does the classical result of Roberts, Gelman, and Gilkes apply to it? And it doesn't. And it's even more surprising than that. For almost every fractional Brownian motion path, the optimal scaling rate for proposal variance in random walk metropolis that should be used with this target is not 1/n, as in the classical result. Is rather than that, it's this thing here. This is worse when in the usual case h would be equal 1, and we would get 1/n here. But instead, it turns out that the best rate to scale the variance is L squared divided by n to 1/h. And on top of that, for any fixed h, we can optimize what's the best acceptance rate. And this is the graph that we get. For various h's here, you get a different number, what fraction of proposals should you optimally accept. And for example, at 1/2, you should accept 7%, and at 1/4, you should optimally accept only 0.7% of proposals. So surprisingly little. Now, you may say that at this stage, I mean, this is all interesting and all that, but this has no practical value. Well, consider the following example. So take another target, another one-dimensional target that is a perturbation of a Gaussian, but it's not perturbed by a fractional Brownian motion, but it's perturbed by something nice with these parameters. And take a 100-dimensional example. So multiply this target 100 times with itself. Notice that this is completely in the regime of the classical paper of Roberts, Gelman, and Gilkes. This is how the marginal target looks like. It's nice, smooth, everything. And here is the surprising result. If this random walk metropolis chain is tuned to accept 23% of proposals, then it has this expected square jump distance. Just a measure of efficiency of the method. And this corresponds to the blue graph. The first coordinate of this thing is depicted in blue. And if you tune alpha to be 7.7%, you get expected square jump distance, which is 5 times better. This corresponds to the red graph. So even though this is in the correct limiting case, even at 100 dimensions, this still behaves much more like this obscene rough cases than it behaves like the classical cases covered by Roberts, Gelman, and Gilkes. And here, so the red graph is the better one, and I'd like to point out this interesting behavior that happens, that the chain gets stuck in local modes for large periods of time, hundreds, maybe thousands of steps at a time, which seems really inefficient, but still performs better than the other one. I'd like to finish with some advertising. This is the archive paper connected to the talk that has just been accepted to Annals of Applied Probability. In it, we also covered the Mala case, and where we were successful to prove that even though you need only one derivative to run Mala, you need 3 derivatives for it to behave in a classical way. Further to that, we develop a framework capable of addressing optimal scaling questions that is very nice and might be of interest to people. And we also develop a generic way to construct counterexamples for optimal scaling results. That would be everything. Here's the list of references that was mentioned in the talk. Thank you for your attention.